Okay, so today we're going to talk about chapter 19, and we are going to break this virtual lecture up into 3 different parts. So there'll be 3 different videos in hopes to keeping these videos shorter than longer. So we are going to be discussing the cardiovascular system, but more specifically blood vessels today. So let's get started. So our blood vessels are going to be the pathways that blood will flow to circulate throughout the body. So it's going to be that delivery system of dynamic structures that begins and ends at the heart, and it also works with the lymphatic system to help circulate fluids that the lymphatic system will pick up and deposit into the cardiovascular system. 3 main structures that are going to make up our blood vessels will be arteries, capillaries, and veins. Arteries are going to be the structures that will carry blood away from the heart. And I'm sure most of you have heard, but if you haven't, an easy way to remember this is that arteries begins with an A and they carry blood away from the heart, which starts with an A. Most of the time, arteries are going to carry blood that is high in oxygen to circulate through the rest of the body. Also, they will carry low oxygenated blood to the lungs to pick up oxygen to circulate back through the heart so that we can circulate it into the systemic circuit. And we'll talk about that in a little bit. Capillaries is going to be the second type of blood vessel structure that we have in our bodies. They come in direct contact with tissue cells, and they are very, very, very thin. And we'll discuss this in more detail. Veins are going to be the last structure of blood vessels that we have in our bodies. They're going to carry blood to the heart. In most cases, veins are going to carry blood that is low in oxygen back to the heart so that we can get rid of the CO2 and pick up more oxygen. And then and then when we're actually talking about blood flow through the heart, there's a set of veins that are actually going to carry oxygenated blood back into the heart so that we can carry that blood out into the systemic circuit. So here we have an overview of the relationship of blood vessels to each other and to the lymphatic system. So if this is our heart here, our arterial system is going to carry oxygen, high content blood throughout the systemic circuit to all of our organs and things like that. Our arteries are going to be branched off into, arteries will branch off. So they'll go from very large structures into smaller structures. So our larger structures that will carry high oxygen blood throughout the body, we're going to call them arteries. So we have an example of an elastic artery here, muscular arteries. And then as they get smaller, we tend to call them arterioles, which we see down here. So we go from a very large structure of arteries, then we go down to arterioles. Then when we get to our actual capillaries that we have here, these will be the very, very thin network of blood vessels that will come in direct contact with our tissues. And they will then deposit all oxygen and nutrients to our tissues, pick up CO2 so that we can circulate that back into the heart. And then so from the capillaries, we go from very small veins that we call venules. And then as these venules get larger, that's when we transition them into veins. And from small veins to large veins back into the heart. And like we said before, in most cases, our veins are going to carry blood that is low in oxygen back to the heart so that we can pick up oxygen and recirculate high, rich oxygen blood throughout the body. Notice how our lymphatics are going to connect in association with our blood vessels. So here we see an example of lymphatics that are attached to a vein. So they will then be able to deposit their fluid into the venous system so that it can circulate back into the heart. Okay, so let's talk about the structure of a blood vessel. So all vessels contain a structure that we call a lumen, which is basically an opening. So if you're looking at a blood vessel, kind of looking at it dead on, that central blood containing space or that blood opening is what we call the lumen, and it's going to be surrounded by a wall. And so the walls of all vessels except for capillaries are going to have 3 layers. We can also call these layers tunics. So working our way from innermost layer to outermost layer, we have the tunica intima, which is the most inner layer of our blood vessels, the tunica media, and then the tunica externa. If we're talking about capillaries, because they're so thin, they're not going to have all three of these layers. They will, though, have an endothelium with a sparse basal lamina. So very thin structure. And you might ask yourself, why would the capillaries not have all of these layers? And take a moment and think about it. If we're diffusing oxygen and nutrients into our tissues and then taking out CO2, we don't want a whole lot of layers for these items to have to diffuse through. So it makes sense that our capillaries would have a thinner structure so that we can diffuse these products in and out of our tissues quite effortlessly. So starting with the tunica intima, like I said, it's the innermost layer that is in the intimate contact with blood. So if that kind of helps you to remember it. It's going to be composed of a layer of tissue that we call the endothelium. And this is going to be composed of simple squamous epithelium, which makes sense. Very thin layer, easy to diffuse products in and out of it. The endothelium is going to line the lumen of the vessel. So remember that lumen is that central opening, and it will be continuous with the endocardium, which is the inner layer of the heart. It's going to have a slick surface to reduce friction because, of course, anytime we are diffusing items across a surface, we want that surface to be pretty slick so that we don't have friction. And associated with the tunica intima, we have the subendothelial layer. And this is going to be a connective tissue basement membrane found only in vessels that are larger than 1 millimeter. Just as some extra information. Going to that middle layer of a blood vessel wall, we have the tunica media. This is going to be composed mostly of smooth muscle to allow for contraction and relaxation. And also it will contain sheets of elastin to further assist with the contraction and relaxation, because we know that our blood vessels can dilate and they can also contract. So this middle layer is going to consist of that smooth muscle to allow for these things to occur. It's going to also consist of sympathetic vasomotor nerve fibers that will innervate this layer so that when we need to contract the layer or expand this layer of the blood vessel wall, we can do so. We say that a blood vessel that has a decreased lumen is experiencing vasoconstriction, and then a blood vessel that has an increased lumen is going to experience vasodilation. The tunica media is going to be the bulkiest layer responsible for maintaining blood flow and blood pressure. And it makes sense because if this is a layer that is consisting of smooth muscle, this is also the layer that's going to either constrict or dilate, then it would make sense that it's going to be in control of blood flow and blood pressure, because we know that blood pressure and blood flow will be directly affected by vasoconstriction, vasodilation. The most external layer of a blood vessel wall will be the tunica externa. It's also called the tunica adventitia. It's composed mostly of loose collagen fibers that will protect and reinforce the wall and then anchor it to its surrounding structures. It will be infiltrated with nerve fibers and lymphatic vessels, and large veins also contain elastic fibers in this particular layer. Vasa vasorum is going to be a system of tiny blood vessels found only in larger vessels, and they function to nourish the outermost external layer. So here we have a diagram showing us the generalized structures of both arteries, veins, and capillaries, or all three, not both. So if we're going to start with our artery, notice that, like I said, that central opening, that space that blood will be flowing through is what we call the lumen. So we notice that, or we see the lumen in both the arteries and veins. Notice that the lumen is going to be larger in veins compared to arteries. Now, if we look at the three layers, here's our tunica externa. Notice that the externa is a little bit larger in veins as well. Then we have the tunica media, that middle layer. Notice that the tunica media is much thicker in arteries than it is in veins. And then here we have the tunica intima, which is going to be all three of these layers here as well. Well, three of these layers in arteries, and then two of these layers in veins. So notice that structurally arteries and veins are different. Although they have all three layers, they do look different based on if we are looking at an artery or a vein. And then if we look down here at the capillary, notice that the capillary only has pretty much two layers that make up a capillary. A basal membrane that's going to support endothelial cells. And once again, we want the capillaries to be very simple in structure so that we can diffuse materials across the capillaries quite easily and effortlessly. Okay, so starting with arteries, they are going to divide into three groups based on their size and based on their functions. So we start off with elastic arteries. So they are thick walled with large, low resistance lumens or low resistance opening spaces that will allow blood to flow through. The aorta and its major branches are also called the conducting arteries because they conduct blood from the heart to the medium-sized vessels. We find elastin in all three tunics, mostly in the tunica media, and they contain substantial smooth muscle, but inactive in vasoconstriction. So simply saying that although they contain pretty great amounts of smooth muscle, these smooth muscles are inactive when these arteries are undergoing vasoconstriction. Elastic arteries act as pressure reservoirs that expand and recoil as blood is ejected from the heart, and this allows for continuous blood flow downstream even between heartbeats. So basically, as blood is being pumped from the heart through the aorta and through these larger blood vessels, the pressure is going to allow for these arteries to expand so that we can have consistent blood flow through these large structures, even between heartbeats, so that we don't have an interruption of that. Elastic arteries are then going to give rise to muscular arteries. So we go from these large vessels or these large structures that we call elastic arteries, and then we give rise to muscular arteries. They're also called the distributing arteries because they're actually going to deliver blood to body organs. Their size range from about their pinky finger size to pencil lead size. So these muscular arteries, I think muscular, I'm like, oh, strong and big, but they're actually pretty small, pretty small. They account for most of the arteries that we have named over time. They have the thickest middle layer of their blood vessel structure, and they also have more smooth muscle, but they have less elastic tissue. And they are active whenever our arteries are undergoing vasoconstriction. So we go from elastic arteries to muscular arteries now to arterioles. So they are the smallest of all arteries. And the larger arterioles contain all three tunics, but as these arterioles get smaller and smaller, we're going to lose some of these layers. The smaller arterioles are mostly a single layer of smooth muscle surrounding endothelial cells. So we go from these smaller arterioles that will have three layers or three of these layers of a blood vessel to eventually just having a layer of smooth muscle that's going to surround endothelial cells. These particular structures are going to will control flow into the capillary bed. So basically, these smaller arterioles are going to lead directly into that capillary bed network that will then distribute nutrients and blood and oxygen to tissues directly. These arterioles are also called resistant arteries because the changing shape of the structure will also change the resistance to blood flow. And like we said, they lead directly into capillaries, which we go into now. So capillaries are microscopic vessels. They are so small that only a single red blood cell can pass through it at a time. So essentially you've got blood filtering from elastic arteries, then to muscular arteries, arterioles, and as they're going through these larger arterioles that are these large structures, blood can kind of, walk through the door side by side. So imagine, you and a couple of friends are going into the mall, you go through the opening doors, maybe all four of y'all can walk through them at the same time. Equivalent to going through the elastic arteries, muscular arteries, maybe even still in the arterioles. So then we go from, a large door down to maybe a door where only 2 people can walk through. So maybe this is now getting into the smaller arterioles. But then when we go into the capillaries, everybody now has to enter one by one because the door is so narrow that we can't stand side by side. So that is equivalent to how blood is going to flow through capillaries. The walls are just a thin layer of the tunica intima, excuse me. So we only have endothelial cells that will then be surrounded by a basement membrane. We have associated with capillaries parasites, which are spider-shaped stem cells that will help to stabilize the capillary walls, control the diffusion of substances in and out of these capillaries, and play a role in vessel repair. So should a capillary be damaged, we have these parasites that will then be able to replace those cell components so that the capillaries can still function properly. They supply almost every cell except for cartilage, epithelia, cornea, and the lens of the eye. So basically, our capillaries are going to supply essentially every cell in our body with blood, except for those areas that do not have blood vessels, which will include cartilage, epithelia, cornea, and the lens of our eyes. In terms of functions, capillaries are going to function in gas exchange, so the depositing of oxygen, picking up of CO2. They're going to function in exchanging nutrients, waste, hormones, anything that's going to be exchanged between blood and interstitial fluid and the tissue is going to occur through the capillaries. So we have different types of capillaries based on what we need for them to do. So all capillary endothelial cells are joined by tight junctions. Remember, tight junctions are those structures that we do not want substances to be leaking out of. And so these cells are going to be joined by tight junctions with gaps called intercellular clefts. These clefts are going to allow passages of fluids and small solutes. And of course, the tight junctions will ensure that any of these fluids that are passing through these clefts do not leak out into the surrounding space. We have 3 types of capillaries. So we have a continuous capillary or continuous capillaries. They are abundant in skin, muscles, lungs, and the central nervous system. And they are pretty unique in structure when we get to the brain because they help to form the blood-brain barrier that will totally be enclosed with tight junctions and no intercellular clefts. So we don't find these structures when we're looking at continuous capillaries in the brain. So here we have an example of continuous capillaries. In terms of their structures, they are the least, they are going to allow the least diffusion of substances across the membrane, and yet they are the most common type of capillary that we have in the body. So here we have an example of a pericyte. Remember, this is going to be a stem cell that will help to repair our blood vessels or our capillaries when needed. Here's going to be the lumen space with a red blood cell in it. This is going to be our basement membrane, this light blue structure that we have here. The endothelial cells are going to be the yellow structures that we find here. And remember, and here we have an example of, where's my mouse? Here we have an example of a tight junction. What I want you to remember about the continuous capillaries are that they are abundant in skin, muscle, lungs, and the central nervous system. I want you to know that they are the most common, that they allow for the least amount of diffusion, and that they often have associated pericytes associated with them. They have pinocytic vessels that will ferry fluid across the endothelial cells. So essentially, and we'll get to this in a little bit, the pinocytic vessels are going to be a way that fluid can get into a blood vessel, and we'll talk about that in a little bit. The second type of capillary that we have in our bodies are going to be the fenestrated capillary. These are found in areas involved in active filtration, like our kidneys, absorption, like our intestines, or in endocrine hormone secretion. With fenestrated capillaries, the endothelial cells also contain what we have, or what looks like a Swiss cheese-like pores that we call fenestrations. This is what allows for substances to diffuse across the capillary. And so if we look at a fenestrated capillary, the fenestrations are going to be substructures that look like these. So they're like these porous structures that we find in the capillary that will allow for more diffusion across the capillary wall. So literally think of like Swiss cheese and the pores that you see in Swiss cheese. That's what the fenestrated capillaries look like. Then the last type of capillary that we have is the sinusoidal capillaries. These have fewer tight junctions. They are usually fenestrated with larger intercell clefts, and they have what we call an incomplete basement membrane. These types of capillaries usually have a larger lumen, and we only find them in the liver, bone marrow, spleen, and adrenal medulla. Blood flow through these types of capillaries is pretty sluggish, but this also allows for time for modifications of large molecules and blood cells that will pass between blood and tissue. And then also in these types of capillaries, they contain macrophages in the lining to capture and destroy any foreign invaders that might actually be trying to get into or out of our tissues. And so here we have an example of this type of capillary, a sinusoidal capillary. And as you can see, the basement membrane is incomplete. It doesn't totally enclose the capillary. And we've got some fenestrations associated with the capillary. Look at the lumen. It's much larger than the lumen that we have seen in the other two types of capillaries, and they have fewer tight junctions as well. So they've got some tight junctions, but just not as many. Okay, so the capillary bed is going to be an interwoven network of capillaries. So when I think of a capillary bed, I think of just this network of structures that are going to be between the arterioles, the system that's going to be delivering high oxygen rich blood to our tissues, and also the venules that will be taking away low oxygenated blood back to the heart. We say that circulation through capillary beds is going to be micro because flow of blood through the bed is going to occur from the arteriole, through the capillary network, then through the venules. The terminal arteriole is going to be a branch off arteriole that further branches into about 10 to 20 capillaries or exchange vessels that will form the capillary bed. And at the capillary bed, that's where we have the exchange of gases, nutrients, waste, hormones, and things like that. Capillaries will then drain into a post-capillary venule. So in a sense, if we want to take this bigger picture, we're going to go from the heart through elastic arteries, then to muscular arteries, then to arterioles. The last arteriole that will then drain into the capillary bed will be a terminal arteriole. Blood will then flow through this capillary bed and then exit out of the capillary through a post-capillary venule. Does that make sense? I hope it does. If it doesn't, just let me know. So flow through the bed will be controlled by a diameter of a terminal arteriole and upstream arterioles, meaning that flow through the capillary bed is going to be determined by the size of these terminal arterioles. Then we also have local chemical conditions and arterial vasomotor nerve fibers that will then continue to regulate the amount of blood that will enter the capillary bed. Because when you think about it, if blood is flowing through the capillary bed to function in the exchange of gases and nutrients, hormones, we don't want blood just like flowing through really fast. That doesn't give us a lot of time for these processes to occur. So we want to regulate the control of blood so that as blood is flowing through this capillary bed, we can make sure that things that need to be deposited into tissues get into the tissues, and things that we need to take out of those tissues get out of those tissues. Arteriole will dilate when blood is needed. So essentially, when we need blood to flow through the capillary beds, the terminal arterioles will then dilate to allow for blood to flow through. And then when we don't need any more blood to flow through, or not as much blood to flow through, it will constrict to shunt blood away from the bed so that we don't have too much blood flowing through, or no blood flowing through at all, depending on where the capillary bed is. So here we have an example of our arteriole, our venule, and then our capillary bed. So when we want blood flowing through the arterioles, we want blood flowing through the capillary bed, the arteriole will then dilate. Blood will enter into the capillary bed here, flow through to the postcapillary venule, and then flow back to the heart. When we want no blood flowing through the capillary bed, then we will have a shunt that will close so that blood, instead of flowing through the capillary bed, will just continue flowing through this arteriole. Okay, so capillaries found in serous membranes of intestinal mesenteries have two additional features that form a special arrangement of capillaries. So we have a vascular shunt and then a precapillary sphincter. So the vascular shunt is going to be a channel that directly connects an arteriole with a venule. So in essence, this will occur if we want to bypass what we call true capillaries. True capillaries will consist of a meta-arterial and a thoroughfare channel, and we'll see this in a little bit. The precapillary sphincter will cuff a smooth muscle surrounding each true capillary that branches off a meta-arteriole. This acts as a valve regulating blood flow into the capillary bed. And this is controlled by local chemical conditions, so it's not innervated. So what are we talking about? What did we just say? So when we're looking at a mesenteric capillary bed, so we've got our arteriole right here, and then these are the precapillary sphincters that are closed. So when these capillary sphincters are closed, they will inhibit blood flow through these capillaries that we are calling true capillaries, and will direct blood directly from an arteriole straight to the postcapillary venule so that we can get into the venules. Whereas, I don't have another picture. I thought I had another picture, but I'll just talk about it here. When the precapillary sphincters are open, that allows for blood to flow through all of the capillaries that we see here, and then eventually go into the postcapillary venule. So for instance, these pre-sphincters are closed, but these pre-sphincters are open. So when the precapillary sphincter is closed, blood is just going to flow directly through this meta-arteriole that we see here. And when you think of meta-arteriole, think middle arteriole. But these precapillary sphincters are open, so now blood's going to flow continuously through the meta-arteriole, but then also flow into these true capillaries that we see here. And then this is the thoroughfare channel that will connect the meta-arteriole to the postcapillary sphincter. Okay, that's it about arteries and capillaries. Moving on to veins. So we like we said before, blood's going to flow from the heart through the elastic arteries, through the muscular arteries, through arterioles. Then we get to a terminal arteriole that will connect us directly to our capillary bed. Now, once blood flows to the capillary bed, we're going to collect that blood through a venule, which we call the postcapillary venule. So remember, veins are going to carry blood away from the heart. The blood that will be carried, not away from the heart, toward the heart. The blood that's going to be carried back to the heart is going to contain low oxygen. So we're carrying it back to the heart so that we can then circulate to the lungs, drop off this low oxygen blood that has high CO2 and pick up more oxygen. So the formation of veins begins when capillaries unite with a postcapillary venule that will then merge into larger and larger veins. Remember that a venule is just going to be a smaller vein. So capillaries will unite to form the postcapillary venules that will consist of endothelium and a few pericytes. The postcapillary venules are going to be very porous to allow fluids and white blood cells into the tissues. Larger venules have one or two layers of smooth muscle cells. So if you remember from a few slides ago, the smooth muscle in veins is very thin compared to the smooth muscles in arteries. Veins are formed when venules converge. So as little venules come together, they're going to form a larger vein. They have tunics, but thinner walls with larger lumens, like we saw before. The tunica media is thin, but the tunica externa is thicker. So remember, the tunica media in veins is thinner than the tunica media in arteries, but the tunica externa is thicker in veins compared to arteries. The tunica media contains collagen fibers and elastic networks, and then the larger lumen and thin walls make veins good for storage vessels. So they're called capacitance vessels or blood control centers or blood storage centers because they contain up to 65% of the blood supply. Pretty interesting fact. So here we see a microscopic view of the lumen differences between arteries and veins. And then this is a diagram showing us the relative proportion of blood volume throughout the cardiovascular system. Not anything that I'm going to require you to memorize, but it just shows you that the majority of our blood is going to be housed in our systemic veins and venules compared to the amount of blood circulating through systemic arteries, arterioles, pulmonary blood, the heart, and capillaries. Okay, so in terms of blood pressure, and I didn't mention this before, but blood pressure is going to be much lower in veins than compared to our arteries, which is why when we have our blood pressure taken, we're going to have our blood pressure taken from an artery. So we know the highest blood pressure that we have circulating through our blood vessels. So blood pressure is lower in veins than in arteries. So adaptations ensure return of blood to the heart. If blood pressure was really high in veins, it would disrupt the flow of that blood back to the heart, which we need veins to do, carry blood back to the heart. We have other adaptations that, or other features that assist in carrying this blood back to the heart. Number one, we have venous valves. So valves will prevent the backflow of blood, basically meaning that instead of blood going back to the heart, these valves will ensure that blood doesn't backflow back into tissues. And it's most abundant in veins of the limbs, which if you think about it, especially our legs, the veins are going to keep blood flowing up and against gravity instead of flowing back, which would flow with gravity. We also have venous sinuses. They are flattened veins with extremely thin walls. They're composed only of endothelium, and we find them in the coronary sinus of the heart and in the dural sinuses of the brain. And here's that same diagram showing us again the differences in structure between arteries, veins, and capillaries. Okay, varicose veins. We've all pretty much either seen them, we might have these, but we are all pretty familiar with them. So if you're not, or you want to know a little bit more, what are they? They are dilated and painful veins due to incompetent or leaky valves. So in essence, when these valves that are in our veins do not properly close to keep blood flowing back to the heart, and they kind of leak or flap open, that's what causes varicose veins. It makes the veins dilated, and that causes pain. So factors that will contribute to varicose veins, we inherit them. And also conditions that we might have that will hinder venous return. So an example could be a person who tends to stand for long periods of time. I know when my mom was younger, she used to waitress, and so she said that she would buy these stockings that were very tight around her legs. And she was like, I didn't want varicose veins when I got older, and I knew I would be on my feet for hours at a time waitressing and things like that. So she would wear basically these compression stockings that would support her legs to eliminate varicose veins. If you are obese or if you are pregnant, these are also conditions that can contribute to the formation of these. Blood pools in lower limbs can cause them, can cause weakening of the valves that can also lead to this condition, and this affects about 15% of adults, or more than 15% of adults. Elevated venous pressures can also cause varicose veins. So for instance, if I'm straining to push out a baby, or if I'm straining to have a bowel movement, that will raise my intra-abdominal pressure, which will result in varicose veins in the anal area, which we call hemorrhoids. And if you've ever experienced hemorrhoids, they're not comfortable at all. At all. So once again, varicose veins are basically veins that are dilated, and they're very painful due to the valves not closing properly properly and causing leakages. Okay, anastomoses. So we have vascular anastomoses. I'm sorry, I just got something. And these are interconnections of blood vessels. So we have arterial ones that will provide a pathway that we call a collateral channel to ensure continuous flow of blood, even if one artery is blocked. And this is very beneficial to us because if we were to have a blocked artery, if we didn't have this additional network that blood can flow through, if we have one blockage, we just wouldn't have blood flow to that particular area, which could be quite harmful and potentially fatal. So we tend to find these in joints, abdominal organs, the brain, and in the heart. We don't find them in the retina, the kidneys, or the spleen. So when you think about it, we have these networks in various vital areas where we need constant blood flow. So we have an arterial venous anastomoses, which include shunts in the capillaries. For example, we have a meta-arterial through a thoroughfare channel. So for instance, remember this diagram that we saw here? Let's say there was a blockage for some reason through this capillary network. Let's just say there was a blockage there. Then we have our saving grace would be this meta-arterial that when we close the precapillary sphincters here and here, we can have still direct blood flow flowing through that area and then connecting back to the venule. Okay, the venous ones are so abundant that occluded veins rarely block blood flow. So we have a ton of them in this particular, we have a ton of these in our veins so that we rarely experience or notice blockages associated with the veins. Okay, I will stop right here and then you can click on the next video for the second part of chapter 19.